Hello dear students, welcome to 𝐂𝐤𝐬𝐿. Today we are going to cover Z transform and its properties. The properties of Z transform are exactly similar to that of the Laplace transform. Okay, so if you remember or recall the Laplace transform, you will be able to see the properties of Z transform also. So we will be discussing the ROC and the properties of Z transform in this lecture. Okay, so we will be discussing the Z transform and the properties of Z transform. So as in Laplace transform, we first discuss the Fourier transform, then we discuss the Laplace. Similarly, here also, we'll first discuss the discrete time Fourier transform, and then we'll discuss the Z transform. So, discrete time Fourier transform. So, discrete time Fourier transform is actually calculated for frequency analysis of any discrete time signal. Okay, so it is given by this. Xn e to power minus j sigma n. N is going from minus infinity to infinity. Okay, so here sigma is the discrete frequency. This is the discrete frequency. Okay, this is a discrete frequency, and xn is any discrete signal. But here the condition is xn should be absolutely summable. Xn should be absolutely summable. That is the condition. Then only we can apply this formula. Okay, so the condition is xn should be absolutely summable. Okay, so this should be always less than infinity. Okay, this should be less than infinity. That is the requirement of this formula. Otherwise, this formula is invalid. If you remember or if you recall, we studied the exactly similar kind of formula in Fourier transform also in continuous time. But there we had integration, here we have summation because it's a discrete signal. Okay. Now, let's move on to what is Z transform. Now, Z is a variable that is R e to power j sigma. So, it is a complex variable. It is a complex variable where R is the magnitude, R is the magnitude and sigma is the angle. Okay, so magnitude and angle, and Z is the complex number. So Z is a complex number, R is the magnitude, sigma is the angle. So as we know that any complex number can be represented as real part plus j times imaginary part, or it can be represented as a magnitude and e to power j angle. Okay, so these are the representation of any complex number, right? So this is Z, and how to find out the Z transform of any signal? How to find out the Z transform of any signal? We can easily find out the Z transform of any signal like this. So to find Z transform of a signal, it is represented by xz and it is written as summation n equals to minus infinity to infinity xn z to power minus n. Okay, this is the formula for Z transform, for calculating the Z transform. Now if you put Z from this to this formula, we will get that this is equal to summation n equals to minus infinity to infinity xn r to power minus n e to power minus j sigma n. Now here we can relate a very important relationship. This is Z transform of a signal, right? This is Z transform of a signal xn. This is Z transform of a signal xn. Okay, and this is Fourier transform of a signal. So if we look at these two formulas, we'll get a very important result. What is the result? We'll get a very important result that Z transform of a signal is equal to Fourier transform of xn r की power minus n. Okay, so if we assume that this is a signal, then we can say that this formula is actually Fourier transform of this signal. Okay, the signal in the dotted line. Okay, so we can say that Z transform of a signal xn is equal to Fourier transform of the signal xn r to power minus n. Okay, now the Fourier transform of any signal is valid only when this is absolutely summable. Okay, so we can say that Z transform of a signal xn is valid only when xn r की power n is absolutely summable. Okay, and here comes the conclusion, or here comes the definition of ROC. If you are able to relate all this with that of Laplace, then it's great, because we have to link the things and then only we can remember. So here we can get a very important relationship, that is Z transform exists. Okay, sorry. That is values of R means this R, values of R for which xn r to power minus n is absolutely summable is called ROC of Z transform. Okay, so remember this formula. This is exactly similar to that of the concept seen in Laplace transform. Not exactly similar. If you are able to link it, then it's great. Okay, so now let's move on. Let's find out the Fourier Laplace transform, sorry, Z transform of some signals. Okay, but before moving to that, let's see one more concept, that is the concept of infinite GP summation. Okay, I hope you all remember that formula. We have seen that formula in class, in our junior classes. Okay, so let's see that formula. It is very important. Suppose we have any GP, we have this summation alpha to power n, where n going from n1 to infinity, means it's an infinite GP summation. It's an infinite GP summation n1 to infinity alpha to power n. So here the summation is alpha to power n1 upon 1 minus alpha. Okay, alpha to power n1 divided by 1 minus alpha. This is the formula. But the condition here is magnitude of alpha should be less than 1. Magnitude of alpha should be less than 1. Okay, so this is the important condition here. Now let us apply that condition in the while finding the Z transform. This condition is very useful while finding the Z transform. Okay, so here we have a signal that is 10 to power n un. Un means let's find out the Z transform. So Z transform says that is minus infinity to infinity 10 to power n un z to power minus n. Okay, this summation. Okay, now since here it is un, so the summation will go from 0 to infinity 10 upon z to power n. So here this is alpha. Okay, so this is alpha and the starting point is 0. So the summation will be 1 upon 1 minus alpha, right? Alpha to power 0 upon 1 minus alpha. Alpha to power 0 is 1. So 1 upon 1 minus alpha 10 upon z 1 upon 1 minus 10 Z inverse is the Z transform. But the condition is magnitude of alpha has to be less than 1. So let us put that condition here. The condition is magnitude of alpha should be less than 1. So we can say that magnitude of 10 upon alpha, magnitude of 10 upon Z should be less than 1. Now what is magnitude of Z? Magnitude of Z. So Z is the complex number, right? Z is this complex number. The magnitude is R. Okay. So it is 10 upon R should be less than 1. R should be greater than 10. This is the ROC. Means it is a region greater than 10. So what is the meaning? If you remember the polar coordinates. So in the polar coordinates, the region will be like this. We will have a circle of radius 10. And the ROC is the region outside this circle. So this will be the ROC, okay? This will be the ROC. Now we have one more case. 3 plus 5j to power n un. So same formula. 3 plus 5j to power n, z to power minus n. The summation will go from 0 to infinity, okay? Zero to infinity. So this will be 3 plus 5j upon z to power n. So if we apply this alpha to power n going from 0 to infinity, the summation will be 1 upon 1 minus 3 plus 5j upon z. Okay. Now here the condition is the magnitude of this term has to be less than 1. Okay. So this is the Z transform. The Z transform is 1 upon 1 minus 3 plus 5j Z inverse. Okay, and the ROC will be that the magnitude of this term will be less than 1. That is the magnitude of 3 plus 5j divided by Z. This should be less than 1. So 3 plus 5j magnitude is under root of 25 plus 9, that is 34. So R should be greater than this. So the region will be outside the circle of radius 34, like this, outside the radius or outside the circle of radius under root 34. So we have seen two cases. Okay, let me write that here. Before moving to the next point, let us conclude it here. So we can see that the general format of the question is like this. A to power n un, if we look at the last two examples, we'll get that A to power n un will have Z transform 1 upon 1 minus A Z inverse. Okay, 1 upon 1 minus A Z inverse. Okay, and the ROC will be, so let us see the pole location. From here we can see that the pole is at A. Pole is at Z equal to A. So ROC will be mod Z greater than mod of A, magnitude of A. So or we can say that R greater than magnitude of A, or we can say that R greater than magnitude of the pole. R greater than magnitude of the pole. Okay. So this is the condition, and this is what one first conclusion about ROC is. Okay. So the first conclusion is, if the signal is a right-sided signal, then the ROC of the Z transform will be R greater than magnitude of the greatest pole. Okay. Here we have the ROC linked with the magnitude of the pole. Okay, and not with the real part of the pole as we have seen in the Laplace. Okay, so it is related with the magnitude of the pole. Okay, so let's move on. Now let's look at the left-sided signal. Now let's look at the left-sided signal. Okay, so here the signal is a to power n u of minus n minus 1. Okay, so first of all, let us see the duration of the signal or the location where it is present. U of minus n minus 1 will be equal to 1, where minus n minus 1 will be greater than equal to 0. Okay, if you remember the formula of the unit step. Okay, so here it will come out to be n is less than equal to minus 1 and 0 elsewhere. So here we can see that this signal is existing from minus infinity to minus 1. Okay, so the summation will be a to power n u of minus n minus 1 z to power minus n equals to minus infinity to minus 1. Okay, so this summation. Okay, now a upon z to power n. Now if you put n equals to minus n, then this summation limit will go from 1 to infinity, and this will be z upon a to power n. Okay, because here also it will reverse. Okay, so using the infinite GP summation, this will become z upon a upon 1 minus z upon a, and if we solve this by taking some common, we'll get the same expression with the minus sign, minus 1 upon 1 minus a z inverse. But here the condition will be that magnitude of alpha should be less than 1. Magnitude of alpha less than 1 means here the alpha is z upon a. So magnitude of z upon a should be less than 1. So it means that r should be less than magnitude of a. So here we can see that we have a very important result. What is the result? The important result is a to power n u of minus n minus 1, the z transform will be 1 upon 1 minus a z inverse with a minus sign, and here we can see that the pole is at z equal to a. So the ROC is r less than magnitude of a. R less than magnitude of a. This is the ROC. Okay, great. Now let's move on to some questions based on this only. So this is a left-sided signal. Okay, this is a left-sided signal, and this is the format what we have got. Okay, so using that format itself, 3 plus 4j to power n u of minus n minus 1, the z transform will be 1 upon 1 minus 3 plus 4j z inverse. The pole location is at 3 plus 4j. So ROC will be r less than magnitude of the pole, that is 5. 3 plus 4j magnitude is 5. I hope all of you remember that. Great. So always remember these two conclusions for Z transform. These are most important, as we have seen in the Laplace, e to power at ut and e to power at u minus t. The two formats most important. Similarly here we have a to power n un. The Z transform is 1 upon 1 minus a z inverse. The ROCs are greater than magnitude of a. And this one, a to power n u of minus n minus 1, minus 1 upon 1 minus a z inverse, and ROC is r less than magnitude of a. Okay, so these two are the things that we have to remember. Great. So the second conclusion, first of all, let's move on to the second conclusion. The second conclusion is for the left-sided signal. If we have a left-sided signal, then ROC of the Z transform is R less than magnitude of the smallest pole. Magnitude of the smallest pole. For the right-sided signal, we have the ROC R greater than magnitude of the largest pole. Here we have R less than magnitude of the smallest pole. Okay. The two conclusions. Now, before moving to this question, let us do this question. Let us practice this question. U of minus n minus 1. Okay. So, let us say 2 to power n un. What is the ROC? What is the Z transform? So, it is 1 upon 1 minus 2 Z inverse. And ROC will be R greater than 2. Okay. R greater than 2 outside the circle. This second one, this is minus 1 upon 1 minus 4 Z inverse. The ROC will be R less than 4. Okay. So, we have a region between two circles. So, is the region valid? Yes. One is saying that it requires the region greater than the circle of radius 2. Other is saying that it needs the circle which is of radius 4. So, this is the region. Okay. From 2 to 4. Inside circle is of 2, outside circle is of 4. So, the Z transform will be 1 upon 1 minus 2 Z inverse. And the ROC is between 2 and 4. ROC is between 2 and 4. Okay. So, this is the point that we have to remember. Great. Next. So, we can see that we have, this is a two-sided signal. This is a right-sided signal and this is a left-sided signal. So, we have a both-sided signal or a two-sided signal. In these cases, we can see that the ROC is between two circles, or the ROC is an annular region between two circles. The ROC is an annular region between the two circles, or we can say that the ROC is between the two circles corresponding to two poles. Okay. So, this is the inner circle is corresponding to Z equal to 2 pole. Outside is corresponding to Z equal to 4 pole. So, in case of a both sided signal, the ROC is between the two circles. We can say that it is an annular region. Annular region. Okay. Now, if we look at one more question that was actually left behind, so let's do that also. The Z transform of a signal that is 1 means it is a constant 1 from minus infinity to infinity. We actually first of all broke this signal or break this signal into two parts. So, 1 can be written as un plus u of minus n minus 1. This will give us 1 from 0 to infinity. This will give us 1 from minus infinity to 0. Minus infinity to minus 1. So, we are getting complete 1 on the time axis. So, if we look at this a to power n formula, we put a equal to 1 here, we will get un. We will put a equal to 1, we will get u of minus n minus 1. So, the ROC and the Z transform will be 1 upon 1 minus Z inverse. The ROC is R greater than 1. Here it will be minus 1 upon 1 minus Z inverse, but ROC requirement is R less than 1 because it is a left sided signal and this is a right sided signal. Now, if we try to combine these two, we cannot combine them. We cannot combine these two. Why? Because the ROC will become invalid. One is saying that ROC greater than 1, one is saying ROC less than 1, but still the ROC is invalid because there is no common region available. So, that's why the Z transform of this signal do not exist. Okay. Z transform of the signal do not exist. Okay. Great. Now, let's move on to one more signal. This is a signal. We can say that there is un minus u of n minus 4. So this signal will exist from, let me show you the location of this signal, un minus 4. So this is un actually, a signal which is from 0 to infinity, it is high or it is 1. Okay, so it is 1 from 0 to infinity. Un minus 4 is actually, it is 1 from 4 to infinity. So if we subtract these two, we'll get 1 only from 0 to 4. So we'll get only one signal is 1 from n equals to 0 to 3, because at 4 also they both will cancel each other. So we'll get non-zero value at 0, 1, 2 and 3 only. Okay, so 1 z to power minus n. So from here we can get the result. Now before writing the result, let me tell you one more summation formula for GP that is very important, and I hope that you all remember that formula. Summation alpha to power n equals to n1 to n2. So this summation is alpha to power n1 alpha to power n2 minus n1 plus 1 minus 1 divided by alpha minus 1. Okay, so this is the formula that I hope you all remember this formula. So if we use this formula here, we'll get z to power minus 0. Okay, then z to power minus the upper limit minus lower limit plus 1, that is 4, minus 1 divided by alpha minus 1 means z inverse minus 1. So this is the Z transform that is very easy to apply. The only thing that you have to remember is this formula. Okay, this formula, the GP formula from N1 to N2. Okay, so simply we can get the result. Okay, so this is the finite duration signal. Okay, this signal un minus 4 will exist only from 0 to 3, only at 0, 1, 2 and 3 only. Okay, so this is a finite duration signal that is existing at only 0, 1, 2 and 3, right? So exactly same property exists for Laplace also. In the Laplace transform, we got to know that the ROC for the finite duration signal is the entire S plane. Exactly the same manner in this Z transform also, any finite duration signal cannot have a finite pole. There are two things. First of all, let us see that for the finite duration signal, the ROC will be the entire Z plane. This property is exactly same as that of the Laplace transform. Okay. And the other property, that the Z transform cannot have a pole at a finite location. So two properties exactly same as that of Laplace. First property is the signal cannot have a finite location pole. Second, the ROC will be entire Z plane. Okay, these two properties are exactly same as the Laplace transform. If you are linking with Laplace transform, then it's great. Next, the last property is also exactly same as that of the Laplace transform, that is ROC can never contain a pole. ROC can never contain a pole. So these are the properties of ROC. Okay, so let us do one example. Let us do one example, 5 to power mod n. So we'll break it into right sided and left sided signals. So it is 5 to power n un plus 5 to power minus n u of minus n minus 1. 5 to power n un 1 by 5 to power n u of minus n minus 1. Okay, so these two are the signals. Let us find out the Z transform for this. 1 upon 1 minus 5 Z inverse r greater than 5, and here 1 upon 1 minus 1 by 5 Z inverse with a minus sign obviously, and r less than 1 by 5 is the requirement. Now here we have two very important points, that this requires the ROC r greater than 5, that requires the ROC r less than 1 by 5. So we can see that there is no common ROC, there is no common region where these two can satisfy, so Z transform do not exist, and ROC is none of these. The ROC do not exist, ROC do not exist, so Z transform do not exist. Remember this, the Z transform of this signal do not exist. Okay, Z transform do not exist. Similarly for this, now this is one will be easier one. It is 5 to power, or we can say that 1 by 5 to power n un, the right sided part, plus 5 to power n u of minus n minus 1. So right sided and left sided, we break it into two parts and then we'll get the result very easily. So this is a to power n un. So the Z transform will be 1 upon 1 minus 1 by 5 Z inverse. The ROC will be R greater than 1 by 5. Okay. This, it will be minus 1 upon 1 minus 5 Z inverse. ROC will be R less than 5. Okay. So now we can see there is a region R greater than 1 by 5 and R less than 5. Yes, it's a valid region. So we'll get 1 upon 1 minus 1 by 5 Z inverse minus 1 upon 1 minus 5 Z inverse. Okay. These two are Z transforms, and the ROC is 1 by 5 to 5. Okay. So I hope all of you are able to get the results very easily. Great. Okay. Now we have seen that this type of signal e to power sigma naught n, or a to power n, let us say a to power n, a to power n kind of signals which do not have any un or u of minus n minus 1, means this is the signal which is from minus infinity to infinity, a to power n. A can be anything, any constant. So a to power n, so first of all we will break it into two parts, a to power n un right sided part, a to power n u of minus n minus 1 left sided part. The Z transform of this will be equal to 1 upon 1 minus a Z inverse, and the ROC will be R greater than mod of A. Okay. This one. The second one, 1 upon 1 minus a Z inverse with a minus sign, but here the ROC, since it's the left sided signal, the ROC will be R less than mod of A, R less than mod of A. So here we can see that the ROC is not common, there is no common region. One requires R greater than mod of A, R less than mod of A. So there is no common region there where the this exists, the Z transform exists. Okay. So the Z transform do not exist for this kind of signal. Always remember that. There are two kind of signals for which Z transform do not exist. A to power mod n, if magnitude of A is greater than 1, the Z transform do not exist. We have seen one example. A to power n, Z transform do not exist. Okay. Z transform do not exist. So these two are the signals for which Z transform do not exist. Okay. Z transform do not exist. Always remember that. Okay. Now, since the Z transform do not exist, Z transform do not exist for this signal, e to power j sigma naught n, the Z transform do not exist. So we can see that the Z transform will not exist for these two signals also. The Z transform will not exist for these two sine and cos also, because sine and cos is written in terms of exponentials. Exponentials, Fourier transform or Z transform do not exist. So the Z transform will not exist for sine and cos also. Okay. So in this lecture we have seen the properties of Z transform, the ROC and other properties. Okay. So we'll end the lecture here itself and we'll continue with the system analysis and other properties of Z transform in the next section. Thank you. Bye bye.